We now move on to session 1 titled Antenna Design Methods and Optimization Tool Hands-on. This session was scheduled to be addressed by Dr. I. Balakrishnan, Joint Director and the Scientist, MEITI, Government of India, and a former CTO of Reliance Jio. However, due to the important official meeting, Dr. Balakrishnan could not able to join us today. In his absence, this session will be handled by technical expert from Entupal Technologies in collaboration with ANSYS India. This session will include an introduction to ANSYS innovation, space and tool capabilities, along with an overview of Entupal products, the basis of ANSYS HFSS tool, a discussion on FG based, sorry, and discussion on 5G based array performance, and a hands-on demonstration on design and analysis of microstrip patch antenna array, exploring key parameters and optimization techniques using ANSYS electronic devices. This session will be handled by Mr. Danush, high, high frequency application engineer at Entubal Technologies Private Limited, Bangalore. Mr. Danush specialized in ANSYS high frequency structures, simulated HFSS, and has developed a strong expertise in tools such as HFSS, Maxwell circuits, multiphysics, and the space claim. He holds a bachelor's degree in ECE from MIT Mysore and has experience in field of high frequency simulation. Beyond his technical expertise, Mr. Danush has been actively involved in conducting workshops, training programs, and faculty development programs across India. He is an ANSYS certified professional in electronics engineering, and his dedication to advanced high frequency simulation technologies has made a significant impact in both the academia and the industry. We are delighted to have him with us today to lead us in the hands on technical session. Over to you, sir.
Good evening, everyone. My name is Dhanush. I'm an HF application engineer in Entupal Technologies Private Limited, Bangalore. So, in entire this workshop, I'll be giving an insight of ANSYS portfolio and what are the products available in ANSYS electronic desktop, and what are the uses of different products like new hertz filters and circuits or EMA 3D cable. I'll be explaining all those products, what are the use case of that, and I'll be showcasing the Intupal overview, what are the products we are dealing with, and what are the products we have, and what are the prototype machines we have, and what are the VNA machines we have. I'll be go through all the domains what we are specializing in. I'll be next. I'll be giving a 5G phased array performance in a slide wise. Then I'll giving a basic insight of basics of antenna designing in ANSYS HFSS. Like everybody know about ANSYS, right? Okay. I'll be giving a just basics how to create a box and how what are the boundary conditions available and what are the ports available and how to assign a frequency. All those things I'll be explaining. First, I'll be giving an introduction about Intupal Technologies, what we are doing, and what are the domains we have. Coming to a vision and mission of Intupal Technologies, we are the holistic solution enabler for system design technologies. And our mission is giving a best technical support with our customers and giving very good technical support for their projects or what about their research works. This is our vision and mission of Intupal Technologies, what we followed in our institution. Next, I give a quick overview of Intupal Technologies, where we are located, what are that. We have very young experience, 14 plus years experience in the market, and we have 130 plus team members across India, and we have a 150 plus corporate customers all over India, and we have 750 college customers, like coming to a tier 1 to tier 3 colleges, all IITs, NITs, all our customers, they are working with the simulation tools, what we are providing with. Next, we have our training arm called Abhyanta. There we providing internship for students, and we will be trained research scholars or engineers, and we provide a certificates from our institution called Abhyanta. There we trained like students, engineers, everybody who are interested to learn about simulation tools. Uh, for internships, it's we can you can utilize Abhyanta platform. Next, we have 12 offices across India. These are the listed below offices where we are looking located in. And coming to market wise, this is a market we are taking care: aerospace, defense, public sectors, research lab, and academy and engineering. These are the market we are looking to it. Next, this is the global recognition what we get from ANSYS or Cadence. We are partner with Cadence also. Next, these are the domains we are specializing in. We are mechanical for mechanical CFD. For those things, we have a simulation tools available with our organization. Next, coming to EMAG, it's for antenna simulations or radar cross sections or 5G phase array and circuits, RF circuits. All those things you can use this EMAG simulations. Next, we have a systems embedded system for doing embedded systems. For those also, we have a solutions. Next, coming to semiconductors, we are giving like semiconductor supports also. Next, coming to industrial designs, for that we have a EOS. We are partner with EOS. Next, we have augmented realities. For that, we are partner with PDC. Next, coming to industrial IoT and IoT, there will be giving our OEM product. There we are giving entire kit for all automated projects. That is our OEM product, what we are provided from Multiple Technologies. Next, coming to power electronics. In power electronics, we will be providing our OEM product called Vivet. There we'll be providing a CROs. All those things we will be providing from this for this power electronics for a low frequency applications. Next, coming to VNAs, there we'll be giving support for vector network analyzers. We are the partner with Android Show. There will be providing shock lines, VNAs, or other VNAs we'll be providing from Android Show. And we have solutions for anechoic chambers also. We providing anechoic chamber for customers who are working with entire like from simulations to fabrications. Next, we have a PCB prototype. There we have a PCB prototype machines called. We are partner with MITS. We providing the prototype machines also, and we are partner with Bungard also. You heard about Bungard. That is also a fabrication machine company. We are partner with them. And coming to additive manufacturing, we are partner with EOS. Next, these are the core values what we followed in our Intipal technologies. We followed with integrity, excellence, agile and responsive, united and focused, and socially environmentally responsible to our customers. I'll be showcasing like electronic product design flow, how earlier design flows are there, and now what are the design flow, what we are following in our current industries. For example, I need to design a microchip patch, means I'll be providing a product specifications to a designer. I'll be providing like all the electric constant, thickness, everything to that designer, and he will be designing that microchip patch and whatever it is, whichever antenna he will be design, and he will be go to a fabrication part. After fabrication, he will be due to the test and verification. There, it will not match my requirement. Again, I need to go back to a designer, and I need to do some changes, and again I go back to the fabrication and testing again. It will take long process, and it's a long design time, and it's expensive process also. Why? Because continuously we'll be changing materials, and take cost for fabrication. It will take too much, like it's expensive process. That's why nowadays we'll be sorry. Hello.
Yes, sir.
Able to see my screen,
Yes, sir.
right, ma'am?
Yes, sir. Yes, sir. You
Yeah,
are
yeah,
audible and we can see the PPT.
yeah. Okay, okay. Thank you for confirming. And earlier days, we have a product specification and we have a designer. Then we go to like that designers have a model and simulation tools. In that, using that simulation tools, you will be create a microstrip patch or any antenna or any phaser antennas. You will be design using that simulation tools. There only will be check our requirements. For example, I need to check a return loss or VSW axial ratio, whether it will match my requirement. Then I'll go for a fabrication, then testing and validation. Next, I'll go to the production. It will, like, it's a short design time. It will take less time comparative to earlier process, and it's a cheaper process. Why? Because we check all those results inside the simulation tools, and I'll be purchase one like the electric material, and I'll be fabricate that. It's like no material waste. Next, it's first time first pass design success. There only we can get a success. Why? Because it will not changes results. It will not vary a results. It will be vary in a like 0.2 or 0.3 that time. So we'll be using this model and simulation tools. That's why this is a new engineering modeling flow what we have followed in our industries from a long back. Next, in a Intupel, we have a solution for like entire antenna designing process. We are there. We are providing a simulation tool. Next, we for fabrication we have a METS. Like for prototyping, we have a METS machine. Next, coming to VNA, we are partner with Android. So there will be giving a support for like vector network analyzers. We'll be providing anechoic chamber also. We'll be giving a complete solution for all those this process. Next, this is a ANSYS academic bundle, HF bundle. What are the products available in it, and what are the uses of this? Coming to HFSS, HFSS is nothing but high frequency structure simulator. It's for high frequency electromagnetic simulations. To do a 3D electromagnetic simulation, it's only depends for a high frequency. Next, we have a low frequency applications called Maxwell. This is only for low frequency simulations. Next, we have SI wave. SI wave is nothing but power integrity and like SI wave signal integrity tools. For that, there we can do power integrity and signal integrity on a PCBs. For that, we will be using this SI wave. Next, we have IcePack to do a thermal analysis in a PCBs or IC package or electronic assembly. We need to do a thermal analysis. For that, we can use this IcePack. Next, we have a Q3D extractor. There you can extract RLC circuits from PCBs, like RLC values from the PCBs. For those extraction, we'll be using this Q3D extractor. Next, we have a MotorCAD. There we can do, that's only for motor simulations. There you can designs like so many motors formats are available in this MotorCAD. There you can extract any BLDC motors and you can check the windings how it will be working. For those simulations, you can use this MotorCAD tool. Next, we have a Sherlock. In that Sherlock, we will be using for life prediction at a component level or board level simulations. For that purpose, we will be using this Sherlock. Then next we have a EMA 3D cable. There we will be using for check the cable harness. For that purpose, we will be using this EMA 3D cable. This is a complete bundle inside electronic desktop, ANSYS electronic desktop. Next, I'll be giving overview of ANSYS HFSS, why we will be using HFSS and what are the solvers available in it. This is majorly HFSS will be using to do a 3D electromagnetic simulations. It's based on a finite element method. Like in an industry, we will be using for EM simulations, and we'll be building a very good gaps between industry and academia. For that purpose, also we will be using this ANSYS. And in this HFSS, we can extract SYZ parameters, and we can extract more like VSWR. All those things will be extracted from this HFSS, and we can extract like electromagnetic like fields for near field or far field. For that purpose, also you can use this 3D ANSYS HFSS. These are the different solvers. What we are any doubts? Okay.
No, for sure.
Okay. These are the solvers we'll be using in ANSYS HFSS. We have FEM solver, finite element method solver. The lambda size of this FEM solver is 10 lambda. This is structure machine giving most accurate results for our like, 10 lambda designs. What we are doing a microstrip patch or any dipole antennas. For those, it will be giving most accurate results and it will give faster results. And it's a frequency domain. Okay, it's a frequency domain. For example, what we can design in using this FEM solvers means antennas, RF structures, PCB structures, or microwave component. It should be the lambda size between a 10 lambda. Okay, next we have IE solver, that is integral equation solver. It's based on MOM, methods of movement, and the lambda size of this is 100 lambda. We can use this for a very large structures. For that purpose, you can use this IE solvers, and it's completely a frequency domain where we can use this IE solvers for what kind of simulations means coming to automotive industries or ships or aircraft to check RF cosite. For that purpose, you can use this IE solver. It's based on a MOM. Next, we have a SBR solver. We call it as a shooting and bouncing ray. There, for example, your structure should be in a conformal mesh. We any rays will be hit to an object, it will be reflected back. For capturing that data, we will be using this shooting and bouncing ray. For example, where we can use this shooting and bouncing ray means a radar cross section and an antenna interface for aircraft and ships and smart home devices. Nowadays, ADAS vehicles are also using this shooting and bouncing rays to check how the antenna behaves inside a car or inside a EV vehicles. For those things, they can use this shooting and bouncing ray. Next, we have a physical optics solvers. Like for this physical optics solvers, it's also a frequency domain, and the lambda size of this physical optics solvers is 1000 to 10,000 lambda. Why? Because we are using very large structures. Means that time you can use this physical optics solvers. Next, we have transient solvers. It is the transient solver is like it's a time domain solver. If you are doing like analysis of electric lightning strike or over an antenna. For that purpose, you can use this transient solvers. For this purpose, you can use this transient solvers to check like ESD, like electrostatic discharges. For that purpose, also you can use this transient solvers. These are the importance of all these solvers in ANSYS HFSS. Next, our this is our strength, like doing an automatic adaptive meshing is our strength. Why? Because no need to mesh your structure. It automatically mesh your structure based on your operating frequency and lambda length, and it will not affect a fringing field. Okay, it will subdivide that structure in a small part, and it will give a most accurate result. It will be subdivided in a tetrahedral shape, and it will not affect a fringing field. That's why automatic adaptive meshing is our strength. Next, we have material libraries. In this material libraries, we have so many materials, include FR4 and vacuum, air. All those materials are available. If you want, you can add your own material once you will be more comfortable with relative permittivity or permeability or bulk conductivity or dielectric loss tangent. Once you aware about all these components, then you can go with your own material and you can rename it. And you can do a thermal modifier also for a plasma simulations. For that purpose also, you can use this material libraries and you can add your own library, whether it's not existing in ANSYS library. This is the advantage of ANSYS HFSS. And in this S parameters, these are the results we can extract in ANSYS HFSS. We can extract S parameter, that is nothing but return loss, and we can extract 3D radiation plots and 2D radiation plots and Smith chart. And you can do a equivalent circuit using this Smith chart. I'll be showcasing in next slides where we can create equivalent circuit using the Smith chart. Okay, these are the results. We can extract more results, but these are the main results what we will be concentrating. And this is a toolkit available, antenna toolkit available in Answers. Uh, in this toolkit, so many inbuilt examples are there. Using that inbuilt examples, then you can change the operating frequency and the outer boundary. It automatically create a structures. Like so many libraries or inbuilt in this. Then based on that, it will be creating an structure and based on your operating frequency. So you can save your time for designing from step by step. So just you can enter the operating frequency and like what radiation boundary required. Okay, next, these are the available antenna types inside that toolkit. We have planar antennas or wire dipole antennas, and so many E-plane, H-plane antennas, horn antennas, everything's are available in it. And we have bow tie antennas, log periodic antennas, and PFA antennas. Sorry, PFA antennas. Uh, we have so many antennas inbuilt here. We will the antennas also there. You can just enter the operating frequency and you can utilize this. For doing an antenna simulations, you can use this. For antenna array simulations, you can use the sensor surfaces to do a 4 into 4 arrays, or 16 into 16, or 32 into 13 array, 32 into 13, or doing a unit cell approach using like periodic boundaries. For those simulations, you can use the sensor surfaces. And coming to HF electronics or ubiquitous means, yeah, everywhere means we are there in a semiconductor sectors. They are also using ANSYS HFSS to do filters or RFIDs or manufacturing sectors. They are also using this ANSYS HFSS. And next we have automotives. There we have like EV vehicles or ADAS vehicle. For those simulations also, they are using a shooting and bouncing race, and they'll be using this ANSYS HFSS there. And next, coming to wireless sectors for antenna and waveguide simulations for ultra wideband. For those things also, you can use the sensor services there. Next, coming to aerospace and defense, they are using for aircraft. They need to check the RF site. For those things, they are using the sensor services. Next, coming to systems, they use for LAN services or consumer electronics and HPCs. For those purposes, they'll be using this ANSYS HFSS. Next, coming to ANSYS Maxwell, there you can do for low frequency simulations. You can solve frequency domain and time domain both for low frequency applications to design a motors or transformers. For those things, you can use this ANSYS Maxwell. These are the Maxwell's applications. What are the applications you can do using this Maxwell? You can do a like BMS, battery management system design softwares, and you can use for a power electronics, and wireless charging simulations. This is a wireless charging simulation. For those simulations also, you can use this ANSYS Maxwell. And rotatory machineries for optimization. All those things you can use this uh, in ANSYS Maxwell. Next, we have ANSYS Designer. There, you can do circuit simulations and system simulators and Smith tool and estimation tools. In this circuit simulator, you can do a DC analysis and transmitter like transient analysis and harmonic balance and small signal analysis. Coming to a system simulators, you can do a frequency domain and time domain like analysis in a system domains, system simulators. Next, coming to like planar EM, there you can do interactive MOM solvers, how it will be working in parametric capabilities. Next, coming to a Smith tool. In this Smith tool, you can create equivalent circuits using a Smith tool. For example, you can carry your antennas and you can add your resistors or diodes to an antenna. Then you can take it to a Smith tool. You can get a results. Then you can using that Smith tool, you can do create an equivalent circuits. This is a like GUI of ANSYS Designer, like all-in-one window style desktop, and it's very user friendly. This is a circuit simulator. Just if you want any components in it, like filters or coaxial cables, just you can drag and drop this to a workspace. You can see that components there. For that purpose, this is very user friendly. Coming to system simulators, these are the results you can extract. Uh, like constellation diagram, histogram, and transient plot. I diagram also you can see using the system simulator in a designer part. Next, we have a planar EM. In this, you can see all those results for your antenna structure. This is a Smith tool. What I'll explaining in this Smith tool for your for matching designs, you can use this. If you want to take an antenna structure and you can add a components here like diodes or resistors, you can add this and you can check the equivalent circuits. It will be creating ports using this Smith tool, and it's very user friendly tool. There you can easily drag and drop the components there, and you can export matching circuit with just in a clicks. That is the advantages in answer circuit. You can create a circuit. Able to see here, and you can dynamically link with answers to all the tools available in answers, like for coming to a mechanical to do like heat transfer or structural deformation. For that purpose, you can link with other projects tool to check the deformation using this answer surfaces. You can take your file and you can uh, do all those results in it. Sorry. Next, coming to a Q3D extractor, there you can extract RLC circuits using a PCB structure, and it's like built-in 2D extractor. It's very user friendly there. For that purpose, we'll be using this like extracting purpose. You can use this Q3D extractor tool. And these are the features of this Q3D extractor. You can like matrix results also displayed in this Q3D extractor, and data table plots or exported to any file formats, and like you can export entire circuit model for a circuit analysis. This is the features of this ANSYS circuits, sorry, Q3D extractor. And next, coming to ANSYS SA wave, it's a signal integrity wave. There also you can extract SYZ parameters. If you want to do like PCB analysis or IC packing or generating SPICE designs, circuit models, and if you want to do a broadband frequency sweeps, for that purpose, you can use this ANSYS SA wave to doing FEM coupled for a transmission lines. All those things you can use this ANSYS SA wave. The applications where all we can use this SAW to do a PCB board modeling and simulation. For that purpose, we can use this and this SAW to check the reliability. And coming to electromagnetic interference and compatibility, that is a mandate test for EV vehicles nowadays. For that purpose, also you can use this. You can use in EMI/MC applications. Next, this is a GUI of ANSYS SA wave. There we have electrical property calculator. You can calculate all the components like for like resistor or like conductor. All those things you can calculate it in a single click. So that's the advantages in ANSYS SA wave. And this is all about ANSYS. We are there for accuracy and capacity and the speed. Next, coming to a METS machine, these are the machines we it's available in our Intupel technologies. Coming to 11 lab and Auto lab. Okay, coming to in this 11 lab, no need to like in this 11 lab you can change a bit manually. That's the difference between Auto lab and 11 lab. Uh, for example, you need to design a microstep patch, means you need to change the bits to make an whole. For that purpose, 11 lab is it's not change a bit automatically. Coming to Auto lab, there it's automatically change the bits based on your project time. Okay, it will be fabricated using like all the structures what will feed to a software it's provided by the METs. There it automatically changes the bit and it will be fabricated an antenna structure or PCB structure. Next, these are the fabricated designs using METs. These are the fabricated in our using our machines only. This is coming to VNA. There you can check all those like results. What after fabrication you want to check the S parameter or gain. For those purpose, you can use this vector network analyzers. There you can check all the frequencies and gain, 2D gain and 3D gain. All those things you can check in this vector network analyzer. We are the partner with Android so for this. And coming to conclusion, what are the products we are using with, where in which applications we are working with? We are working in aerospace defense and the medical sectors and automotive systems and semiconductor and IC tracking and telecommunication system. These are the application areas where our tool will be used widely. These are the applications what we are working with. Next, if you have any doubts, please let me know here. Otherwise, I'll be going with next part.
Sir, one question is there in chat box. What is the cost of AutoCAD machines and MITS machines?
Sir, I'll be giving my mail ID, sir. There we'll discuss one on one, sir. For that, I'll be putting my mail ID and contact number in the chat box. Then we'll be discuss one on one on the price and cost wise. We'll be discuss one on one.
Sir, there is one more query in chat box. What
Okay.
models are used in engineering modeling flows?
Like what model means? Like, can you brief about it, sir? Whether it's for like turbulence model or it's from CFD modeling. Just you can give more introduction about it. Then I can address it. Before fabrication in the block diagram. Sir, I didn't get your question, sir. Can you unmute and ask you a question? With a
Hello, sir. Am I audible?
yes, sir. Yes, sir. Yes, sir.
Sir, actually, in AI in design, first you give a traditional way of designing an antenna, right?
Hmm, 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 hmm,
So
hmm,
then you gave like a block diagram in which AI is introduced.
hmm.
So like there you have given the product spec, design, then model.
Yeah, for example, sir, for example, if you want to design a microstrip patch, okay, you have product specifications like dielectric constant and height and the material, all like all of the product specification you have meant you can give to a designer. He will be he have a model and simulation tools. Then you can use that model simulation tools. You will be calculate the patch length and width using the theoretical values, then you can design accordingly to our operating frequency.
There my question is like, so what are the models we are using? Like for example, any like, few models. For example, I'm doing an antenna for Wi-Fi applications. So what models can I
Sir, in
use there?
that Wi-Fi application you can use a meander line antennas, sir. Meander line antennas, like
So where
model in the
AI
sense.
is there
Yeah,
useful?
sir, where.
How can we integrate AI ML in this
Sir,
process?
I'll be showcasing that, sir. I'll be showcasing in like in the last sessions. I'll be showcasing that where you can. We have a Python based simulations also. I'll be showcasing that time possible in the last session. I'll be showcase that where you can integrate with AML and where you can do a like Python analysis or Python code. You can use that and you can create a, like entire structure using the Python codes. I'll be explaining in a last session.
Sir, one more question in chat box. Can we
Yes, sir.
do a
Sir,
complete PCB design process using ANSYS?
Sir,
So,
yes. Once you have more comfortable with answers, you can complete. You can design entire PCB structure, sir, based on standards, PCB standards. Okay. Next, I'll be showing a 5G antenna performance using ANSYS HFSS, and the multiphysics tools. What are the requirement and what are the procedures to do that? I'll be just giving a glimpse and ideas of 5G phase arrays. In this slide, I'll be explaining in this presentation, I'll be explaining about a phased array performance and the concept of installation. We can install in the mast and we can check the results, how we can install the mast and how we can visualize the results, what are the, how the like broadband will be affected and how the building blocks will be affected, and what is the concept of like base station hands off. I'll be explaining in this slide. I'll be like I'll be a little fast. If you have any doubts, you can like stop me there and you can ask your questions. You can put it in a chat box. Otherwise, I'll be addressed in the last in the end of the session. And this is a agenda for this presentation. I'll be giving introduction of ANSYS Electronic Desktop, just a GUI, and coming to 5G phased array workflow from concept to installation, coming to a element design or phase array synthesis or install performance or link margin interface analysis or multiphysics after installing, how it will be deformed. All those things I will be showcasing in these slides. And you can do like automation also, like antenna workflow automations there, where all you can fetch AML and where you can use the Python codes. I'll be showcasing in this PPT. This is a multi-domain, multiple physics. What are the three physics involved to do this 5G phase array simulations? One is ANSYS Maxwell, and one is like thermal and like stress in a mechanical part. In EM fields, we will be using ANSYS HFSS. In ANSYS HFSS, we will be do simulations for adaptive meshing and temperature-dependent materials. For those simulations, you can do in ANSYS HFSS. Coming to mechanical, there you can do a conformal mesh and you can use a transient and steady state thermal simulations. There you can check the heat transfer or the deformation. All those things you can check in the mechanical tool. Next, this is the GUI of ANSYS HFSS. In next slides, I'll be explaining about all this icons. And you can make it all a single GUI in a single windows. You can visualize all the capabilities in ANSYS Electronic Desktop. Next, this is the steps what we use for workflow for a electromagnetic simulation workflow in ANSYS HFSS. First, we'll be creating a model. In a model, we'll be creating a structures of like microstrip patch or anything else. Next, coming to boundaries, there you can assign like perfect electric boundaries, or you can assign all those boundaries there. Next, in excitation part, you can use you can give a port, and in excitation is the part you can give a current for your antenna source. And coming to mesh operation, it's like default mesh, no need to mesh automatically. You can mesh, that option also available in it. Based on length, you can do a meshing. Okay. And next, in coming to analysis, in analysis part, you can assign operating frequencies and the sweep maximum delta values. All those things you can like give the values in analysis part, and you can enter the operating frequencies there. Next, coming to optometrics, there you can do optimization for your antenna, for example, for a specified frequencies or specified length and other width. For those optimization, you can use this optometrics. Next, coming to results, that is a post-processing. There you can see results, like VSWR, XL issue, all those things you can see in the result part. Next, coming to field overlays, there you can check how the electromagnetic distributions happen for a structure, and you can visualize in animated part. These are the applications where we can use this ANSYS HFSS. You can use this for antennas or waveguides or filters or wires or MMI devices or cell phones or biomedical applications, or you can use for EMI applications, EMI-MC application. Using some set of standards, you can use this EMI-MC application. These are the applications what we can design using ANSYS HFSS. You can do SAR rating also. How the like mesh will be affect for like how the accurate meshing will be affect through a structures, how the non-conform mesh affect to a structure. For example, I need to, whether it's non-conformal mesh, for example, I hit a race, it automatically revert back and you can easily identify which object is that. Once it will be a conformal mesh, you can hit a race to a structure, it will not reflect it back, it will be distributed in other directions. So there we're not able to identify which object is that. For that purpose, automatic adaptive meshing is also important. There you can do like you can get accurate results. For those analysis, you can use this finite element analysis in a meshing part. and it will be divided in a tetrahedral shape. This is a like adaptive meshing process. How the process will be taken care inside ANSYS HFSS. First, we will be created a geometry. Next, it will be created an initial mesh, and it will be refined the mesh, and it will be converged the mesh. Next, it will be generated the frequency sweeps. Whether there will be a like error, it will be repeat the process, mesh refinement and solve, and it will be edit the maximum delta values and the frequency sweeps. All those things, these are the background process in adaptive meshing using the finite element analysis in ANSYS HFSS. And next, I'll be showing the concept to installation using this ANSYS HFSS. In this, we are there for like all major physics from chip to ships. Okay, for here we are there for all major physics from nanometer to kilometer to doing and transistors or 3D RFIDs or RFICs or PCBs or antenna element or 5G antenna phase arrays or base station modeling and masked with the base stations, and how the network planning with the base station coverages, how the base station will be coverage with the blocks of buildings, and what are the like errors we are getting, how the like radiation will be distributed. All those things you can analyze using this ANSYS capabilities, ANSYS tools using multiphysics analysis. Next, this is a design workflow for a 5G phase arrays. First, we will be using ANSYS HFSS. We will be create antenna elements and antenna array structures using unit cell concept. For doing a like phase array or unit cell concept, you can use a periodic boundaries. There you can create unit cells and you can do optimization. If we create a structure, we'll be using installed antenna performance. For that purpose, you can use this SBR. SBR is nothing but shooting and bouncing ray. There you can check like antenna housing and how the antenna array will be performed, including this housing on the mast. Whether without housing, how the results will be affected, and with housing, how the results will be affected. Housing is nothing but like coverage of an antenna. Covers of an antenna, we call it as a housing. Uh, there in this SBR, we can check the installed performance with a mast on a base station. Next, coming to a system part, there you can check link margin and interface and coupling and how the beam steer will be happening. For those analysis, you can use this ANSYS SBR Plus and emit tools. Next, next step is to check the network planning and the coverage studies. You can check the network planning with the base station and how the user interfaces will be coupling and how the handoff between one base station to another base station, how the like multiple massive MIMOs are working with that. All those performance you can evaluate using this SPR in this part. Next, coming to a multiphysics analysis, there you can check how the temperature will be affected and how the two-way coupling will be taking place. Once where we can do a thermal analysis, how the fan will be cooling the antenna temperature. All those things analysis we can taken care in this multiphysics analysis part. This is array element designs. This is for a dipole antennas. There you can check. This is antenna where we are using for a creation of 5G phase arrays. For that purpose, we'll be using this dipole antenna, cross dipole antenna elements. It's like all periodic boundaries is applied for this, and we'll be make this as an array. And these are the new features available in ANSYS HFSS to make this as a like arrays for 8 into 8 arrays for a 5G in a 28 gigahertz operating frequency. Then we without housing, how it will be radiated, all those things we can check with using this ANSYS HFSS. And after covering of a radome, how the like all panels will be working, how the radiation will be splitted, all those things you can visualize using this ANSYS HFSS. These are the new features available in ANSYS HFSS, and how the simulations will be taking care and how much time it will be taken for a simulation purpose. Whether it's a 32 GB core, it will be take approximately 3 hours to simulate all these simulations. For example, to install on the base station, how the radiation will be happened. All those simulation you can done in 3 hours. And we have a 128 cores. There you can check approximately 1 hour to do all those simulations. These are the cores based on your system configuration. Next, coming to antenna housing and installed the phased arrays in including house and housing in the mast. This process you can use all those available products in ANSYS electronic desktop. We can't design everything using this ANSYS HFS itself to create and this entire like areas. We will be using the mechanical or structural tools to create all these building blocks or blockages, everything with other multiphysics tools also. ANSYS multiphysics tools. There you can create all those building blocks. We'll be placing an antenna, we'll be placing a mast. For those, you can use all like different physics tools. Next, coming to hybrid solutions, where the finite element method impact to an antenna array structures, how the solution will be combining both solvers in a one design, and how the it will be solve the complex problem will fully couple solutions. All those things you can done in this part. Next, after installed like antennas in a mast, how the 5G base station radiation will be happening and how the like 4G base station results will be get it. In 5G base station, we received less number of side loops and we'll be have a more major loops. In coming to 4G base station, we are getting very more like side loops and very less in a major loops. It will be like the fast we have a 5G network, how the antennas will be beam steer or how the antenna arrays will be happen, how the housing will be covering. All those things matter to get a very proper accurate radiation in a mast. And these are the results in after installed performance in a mast and how the results you can extract from all those like all antennas, how like all particular antenna will be working. All those reasons you can extract after install in the mast. And next, coming to mechanical housing, this is a housing what we using for housing, how we created housing, what are the screw length and weight. All those things will be we have entire specification to create this housing, and how the round corner radome will be affected and what are the results will be changing using the like all those like round corner radomes. And I'll be showing the comparison for like with a free space, how the free space results will be visualization, and antenna with a radome, how with the radome it will be working, how antenna housing and radome will be working. Using this Smith chart or radiation pattern, you can visualize all those results, radiation pattern results. There, then in coming to a free space, the major loops or less and the minor loops also less. Coming to with a radome, we get more side loops and we can increase the performance. Next, with a blue one, it will indicate antenna housing and the radome. It will be decrease the side loops and you increase the major loops and it will be radiated in a more large structure, large part. Next, how the edge effect will be matters for this housing part, how the smooth and the sharp edge will be affected. That black one will be indicate the smooth edge and coming to red one, it will be indicate the sharp edge. This is also make big difference in the radiation patterns. Once you will be coming to a like housing part or simulation part in hands-on, I'll be whether it's possible, I'll be showcasing this how it will be affected to an antenna structure. Next, coming to network planning for user interfaces, how the hands-off will be taken place and how the MIMO will be working there. All those things you can do in this network planning and coverage studies. For example, if you want to see the network planning for a large scale in a simulation part, you can use this SBR solvers. For example, a receiver will be traveling from position 1 to position 2 to position 3. We have a base station in a constant position. How the network will be fluctuated and how we get network loss, all those simulations you can observe in this position 1 to position 3 results. How the like reduced signal strength for a received receiver to travel from different directions and like there will be more blockages in it. How the like network drop will be happening. All those simulations you can then enhance HFSS with the support of SBS solvers. how the antenna fixed will be there. All those things you can visualize in ANSYS HFSS using this solvers, this base solvers. How the base station hands-off will be taken care means how the device, uh, for example, device travel along the street in an urban environment from base station 1 to base station 2. How the coverage zones for two base station, how the hands-off will be taken care with from the base station 1 to base station 2, how the site elevation will be taken care, and how the base station to base station interface will be happen. Using this SBR solvers only, you can like visualize in this ANSYS HFSS using SBR solvers. The device will be traveling from this urban environment to near to a base station 1, from base station 2, from the user will be traveling to base station 2 to base station 1, how the hands-off will be taken care. For example, this indicates this is a user interface. The user will be traveling from base station 2 to base station 1, how the hands-off will be taken care. This is like base station, this blue color indicates a base station 2 and this red one will be indicate base station 1, how the cell coverage will be taken place. It will be coming near with base station 2 to base station 1, there it will be handover. Once it will cross the base station 2 limit, then it will be handover to a base station 1. That is a base station hands-off, how the like user will be hand off to base station 2 or base station 1. Next, how the link margin and interface and coupling models will be taken care. And how the beam forming will be taken place, and how the beam steer will be taken care. And using this, we will be using this RF system definitions to create like RF circuits for this mast insulation using network blocks or building blocks. For those things, we can use this RF system definitions. And how this link margin versus distance will be taken care with interface and without interface, how the link margin and the distance graph you can visualize with interface and without interface, how the results will be affected. This is I'll be showcasing in hands-on. Once I'll be showcasing antenna design structures, I'll be showcasing this link margin results, that how it will be affected like that. I'll be showcasing in that. Next, we have two-wave electromagnetic thermal simulation for a 4G base station arrays. How the two-way coupling will be taken care. All those things you can visualize in ANSYS HFSS with support of a thermal, like steady-state thermal in ANSYS mechanical tools. And how the RF loss will be taken care. And you can, this is for a 5G base station. For example, for a 40 watt input, you can get 4 watt RF losses for based on your input power. And this is for 18 to 8 dipole arrays for millimeter wave for 5G base stations, base station antenna. This will be simulated using the ice pack for doing a thermal analysis. You can check all those, like you can check all the temperature for different materials, like coming to dipoles or coaxial inner cables or outer cables, how the radome will be with the material, how the temperature will, maximum temperature will be there. All those things you can check using this ANSYS ice pack. And you can do thermal management in ice pack. There, to reduce overall temperature, you can added one like 50 fan on a bottom to like reduce the temperature. Approximately after install the fan in using this ice pack ANSYS ice pack simulations, the temperature will be decreased to 68 degrees Celsius. like how the like temperature will be decreased. Those simulations also you can take in place in using this ANSYS ice pack. Once you are be more comfortable with ANSYS HFSS, then you can explore this ANSYS ice pack to do this thermal analysis. Next, how the like antenna performance will be there for after thermal loading. The results will be increased more with thermal loading, before thermal loading and after thermal loading. You can see the major changes using thermal loading and before thermal loading, after thermal loading and before thermal loading. This will be impact in like in two-way coupling. Next, these are link margin simulations after a multiphysics simulation. How without interface before thermal loading or with interface before the thermal loading. All those things you can visualize using this ANSYS HFSS. You can recalculate the like results using this ANSYS HFSS simulations. Next, coming to automation, how automation will be taken care from designing to a beam steer or like unit cell projects, or to create an active S parameters versus a beam steer angles. Based on your required angles, you can steer your beam or gain data, or you can do like phase change materials. All those things you can add using this like workflow automations. There we have an option in ANSYS HFSS. There you can add your AML and you can link with machine learnings to create this automations also. There we have an option to create Python code for creating a structures. We have models for PyAnsys also. There you can uh, create your enter your like codes, and it automatically create an entire structures based on your codes. That option also integrated. Then you can record the response also. That option also available in ANSYS HFSS. And this is a conclusions for like complete 5G phase array like designs for element level to a system level using this multiphysics domain. And this is a conclusion. I'll be for doing a 5G phase arrays. We need to use this HFSS and IcePack to do a thermal analysis, and like SBR solvers we need to use for do installed like to check the building blocks and the coverage and network planning. And we need to use emit to do a link margin analysis and interface analysis. This is complete 5G phased array uh, antenna designs. We have limited time slot, so I'll be hurry with this presentation. You have I'll be sharing my email and the contact number. You can contact me and we can discuss one-on-one uh, for this entire 5G phased array workflow. If you have any doubts, please let me know.
Hello, sir.
Yes,
So
ma'am.
there is
Yes.
a question in chat box. What
Okay.
is the concept of radome, sir? Whether
Sir,
it is related to array?
yes, it related to array means to cover an antenna structure. For example, you can see the base station in the outskirts, right? You will see the base station, right? It will be covered with a structure. That structure we call it as a radome. Any other doubts? You can let me know. If you have any queries, I'll be drop my mail ID is there. You can mail me at any time, and I'll be dropping my contact number. Sir, how long will it take to run a simulation? Sir, based on your designs. For example, microstrip it will take a minute or less than a minute. Based on your project, then we can able to give a simulation time. For real world scenario, it will take, sir, based on your system configuration. Your system have very good configuration like 128 cores. Approximately, it will take 2 to 3 hours to do a simulation. Complete certifications means, sir, that is we have a one more option for learning up. There you can pay for a badges and you can get it there, sir. Any doubts? Please let me know.
Participants, if you have any queries, please use the chat box for asking your questions and queries to Sir, or else unmute and ask the questions. We hope Sir have addressed all your questions, and thank you so much, Sir, for your highly informative, engaging session and answering all our questions. It was indeed a valuable lesson for us and an experience for all of us, offering a deep insights in ANSYS tool. With that, we now conclude the session 1 of our FDP program.
Thank you for providing this opportunity. I have two more sessions on 29th and 30th. There I'll be showcasing some hands-on session there with a basic example. Like all are or new to answers means I'll be showcasing some basic designs coming to answers. In answers such as this, like microstrip patch or whether times possible. I'll be giving insight for doing a like matching network or equivalent circuit. I'll be showcasing it. I'll be discussing that, Preeti ma'am. I'll be discussing one-on-one on this. You can take my contact and email. You can like reach me out. We can discuss on one-on-one.
Thank you, sir. Thank you so much. And moving ahead, we are honored to continue the day proceedings with a technical talk delivered by Ms. Anto Amala Arulraj, Senior Staff Engineer in the Memory Division at Samsung Semiconductor, India. As Anto has been contributed to semiconductor industry since 2021, where she plays a key role in memory firmware design and validation with a focus on high performance NAND storage system, security features, and the firmware optimization for next generation memory solutions. She brings with her extensive experience from her previous tenure as a firmware development engineer at HCL Technologies, where she contributed to Intel Corporation's solid state devices projects, focusing on firmware features development, performance optimization, and developing across and debugging across multiple firmware modules. Her technical expertise spans embedded firmware, programming, agile methodologies, and tools such as a Green Hills Multi, Eclipse, Atlassian Tool, and a CST Microwave Studio. As Anto's professional interest includes solid state devices, antennas, and advanced memory technologies, and she continues to contribute actively to innovation and development in the field of firmware and storage engineering. We are delighted to have her with us today. Please join me in welcoming her as she delivers her technical speech. Over to Ms. Anto.
Good evening, everyone. So this is Santo here. Uh, like uh, uh, to a little bit about me, it's like I've been working in my MTech projects on antennas and design and development. Later in when I moved to my professional career, I started with memory storage. This is a brief about me. Today, like I would give a brief introduction about what are the points to be noted out for an antenna design development in an industrial perspective. These are the learning points which I gained during my career over here, the current industries. So so the thing is like when I say that is like antenna design and development more and more I think when I started my MTech project with antenna design and development, it was all like how you make your antennas very small, how my bandwidth is going to get incremented, how is my efficiency is going to go ahead, how is my gain is incremented. These are all the points when I looked it in my MTech project I all think about. So that's how the design starts up. But thing is like when you get into an industry perspective, it's not about the gain, the bandwidth, nor the frequency which we operate. There are multiple instances to be taken into account when we design an antenna. So I would like to give a like very short note on the points which we should look into while we design an antenna, or like how do we showcase the antennas, what kind of design I should come up with. So such kind of stuff sorry, I was on a mute, sorry. So like when we consider the antenna for the in a case of a mobile development, so we should consider the nearby components which is going to be placed around the antennas. So whenever we design an antenna, we should not always think about a case like how my antenna is going to operate about, rather than thinking about how my antenna is compatible with the nearby equipment. So it's not about like the antenna we design, it's an electromagnetic component which is going to emit the radiations. So how it is going to impact the nearby components. So this is the first thing we should look into it when we design an antenna. So this is the one where we many like initially when I started designing my antennas, I lacked about this, because of which like when we start to design thinking in a way, okay, when I move this, my electrical length reduces, so I get my very good frequency of operation. But then when I go ahead with my lesser electrical thing, I just go with something like when I have less electrical length, I might end up with my radiation efficiencies getting poor. How to improve that? When we go in such a manner, it is always like I'm always much worried about my own design of antennas. So to come out of it, we should always think in a way like how we design an antenna based on the mean to say like mean to say like how we should design an antenna in such a way like considering the nearby components. Like I didn't have any presentation being prepared since as I was on a business trip for Korea, so I'll just given like brief introduction about in industry perspective. Sorry about that actually. So that's the first thing we want to consider, because I would give you a real time example where it makes a sense. Let's say when you design an antenna, when it starts to emit radiation, think about the temperature as a component. When you consider temperature as a component in industry, whenever any product is being designed, the first thing we do here is thermal simulation, which most of the time when we design an antenna in any of our papers, we wouldn't have this point as a thermal simulation as an important point, because this makes a huge impact, and we have multiple times redesigned our work because of the thermal simulation results. So this is the first thing we should consider whenever we do a design. We should have a visually see my simulation result of a thermal simulation, how it is going to impact. And the first thing is like when you do a thermal simulation, we should think like where is my temperature area is getting more and more hotter, and what point it is getting hotter. So in such a case, when I keep another component of, let's say like on my receiver or some other component nearby to it, how it is going to make an impact. So this is like an impact study we should think about. This is the first thing, like I would say like in a thermal simulation kind of stuff. So this is the one like I would like to the first highlight on a point is a thermal simulation. The second thing, the new technology now we are working on industry is a metamaterials. So when we consider metamaterials, metamaterial is like now people started working on the clocking technologies and metamaterials and different kind of materials being used. But when I speak about all these things kind of stuff, it's all my electrical component. So the second thing is like when I choose my material, whether for what kind of application am I choosing the material, that is the second thing we should think about, rather than choosing a common material which everyone uses. Whenever we design or whenever we go ahead with some kind of research or something on it, think about the application, what I'm going to use and what kind of material I'm going to use. In case of industry, like there is no rocket science concept of using a very good material like I use this and that. It's not like that. It's like a basic, it's like a very when the substrate we use is like it's not at all like that high level. It is actually, it's a minimal, like whichever is readily available. So that is the thing we should take into consideration. So that is the one we have to look into. And when we started using the metamaterial, we should always look into a perspective of the radiation perspectives, because the metamaterial, though it helps to increase my radiation, there is a huge conflict on my efficiency of radiation. So this is the second thing we should take into consideration. And the fourth thing I would say is like miniaturization. So when I speak about antenna miniaturization, antenna is like kind of like when you design, it's like my length and a frequency, or it's like inversely proportional. So when I want to make a antenna for an higher frequency, I can design it in a, let's say, electrical length. When I want to design an antenna for a lower frequency, like let's say like mobile mobile band or something, we should, when I say it's a mobile band or something, my frequency is very less. In that case, my antenna, as per my electrical, like as my mathematical model, my antenna looks very big. But what kind of stuff can I do it to make it to reduced? So that should not become like a way of like cutting down my antenna design or doing some kind of, okay, let me reduce this side so my radiation goes this way, so my electrical length is reduced. It's not the way at all. So the first thing we should think is like, when you design an antenna, first try to visualize like how my electrical wavelength propagate from one place to the other place. That is the first thing we should look into in case of an electrical length perspective. So this is the fourth point I would like to highlight. And the fifth point I would like to highlight is on the Fifth point I would like to highlight is on the radiation. So when I say like radiation, let's say like an automobile industry case, automobile is like a very stringent industry, I would say, because the way we work here for an automotive product is very difficult. What in sense it's a very difficult is like, the automotive product doesn't comes like a mobile handy we have it in. Automotive is full of a conductor being packed up like in a car or something. On the top I'm going to place my antennas. And so when it comes a bigger mass body of an conductor and another mass body of an antenna to it, there are so many coupling losses and kind of stuffs going to happen out. So when we think about in such a case of when I keep my conductor and another conductor, how my real radiation is going to work through. So this we should think in our mind or perspective. So the first and foremost point I would highlight is like, on what kind of basis am I going to design an antenna? Rather designing antenna and thinking of a way to put it into somewhere, first let's go back to the way like, where am I going to use this antenna? Rather blindly saying in 5G technologies, or I'm going to use for millimeter wave communication, rather we should think of a way like, am I going to use in an automotive product? Am I going to use in a base station? Am I going to use in a mobile product? So when we try to answer first question of that, that is the first way we try to design an antenna. We get an answer for everything. When you say base station, I want an array of units. So when I say it's a mobile unit, I should have a like and bidirectional. When I say it's automotive, I should have a MIMO kind of pattern of connectivity of all sides. So this first question, when you try to answer, this is the first and foremost way of designing the antenna. The next part which I told you about is like the design way. The design shouldn't come up with some random way of seeing a paper and drawing it up some stuffs and going ahead, okay, let me change this, let me change this. It's not at all that way at all. When you keep reading the paper, you get so many designed by each and everyone, and everyone have their own perspective of the design. So when you start with any kind of design, think about the electrical length. That is the first and second thing you should think about. Once you consider electrical length, you go ahead, okay, let's do a mathematical model of electrical length, how it's my antenna is going. Like when I first told about the industry perspective, let's say it's an automotive product, I'm going to keep my it says in automotive clearly, it says my antenna can present only in the this much, let's say like x into y space only, it cannot go beyond that. So I should design my antenna into x into y space. That is the first thing. So when I say x into y space, how am I going to control my electrical length? So that how am I going to increase my electrical length? That is the next thing I should look into. So when I told next we have to like taken into consideration is the substrate. The I mean to say like, which substrate am I going to use? So we cannot use like someone says FR4, someone says this is good, that is good, some paper suggests something. Don't go with that. Think about the application, where am I going to use it? Take a research on the way, like suppose an automotive says an X substrate, I should go and look for that substrate and try to simulate my modeling with that. Only then when I would be end up with something, a product that is really going to be implemented in a market kind of. The next thing I told about is the bandwidth and the radiation efficiency. So when I say bandwidth and radiation efficiency, think about a way how my antenna has to work. It's like very simple. Antenna is like, I want to have it in my all direction or in one direction, or how am I going to have the antenna beam to look like? When you have such kind of, okay, my beam shouldn't have a back pattern, my beam should have been an it should be an unidirectional or bidirectional or all direction. When you think about this point, we will have an idea. Okay, when you design the first antenna itself, try to look at your antenna where and all it is getting reflect, it is getting your beam is going through it. So when you see like, okay, my antenna is somewhere, my electrical length is going to a larger extreme, so I have my more bandwidth like beam going ahead. When you see such kind of stuff, you get to know, okay, this is the where my antenna is losing its efficiency, let's do something. When you want to reduce electrical length, think about the multiple ways of we can read multiple papers and come to conclusion. Like we can use, many would have used metamaterial, many would have used a fractal model, many would have used a half plane half ground model. So there are many ways to reduce it. So we can try to identify which is the perfect way to reduce that kind of back lobes, and perfect way to increase my radiation efficiency. So these are the like minimal like I would say, like these are the very key major points we should consider when we do a design and antenna in case of industry perspective. Because in case of industry perspectives, whenever we end up with something like a design and development, or as a kind of researcher, or when we go with some paper kind of presentation or something, when our antenna, how come we can be different from the other person, is the only thing is like how my product is going to be an industry efficient. Can I deploy that product into an industry perspective or not? That is the foremost thing we should look into it. So I would say like these are the major points we should cover, and just the major points we are also working into it. So I couldn't say about what kind of substrate and what kind of material can be used, because it is I cannot comment on that. It's like it's a confidential things. And so I would can say like a brief about what is being used and what not to be done. So this is all about the things which I have an experience in my industry. So I would have like a brief discussion. I would want to just give a highlight on it. So it was like completely I couldn't give a more idea information on it, since I was like on a business trip. So I couldn't give a complete presentation on that. So this is just like there's a kind of a small talk to show visualization how an antenna works in an industry perspective. So this is all about things I want to share with you people. Thank you for the time. Yeah, I'm done with my presentation.
Thank you so much, ma'am, for your valuable perspective on antenna design. We truly appreciate the clarity and the depth with which you have shared your expertise. With that, we conclude this technical session. Thank you once again, ma'am, for taking time to be with us despite being in your official business trip.